Today we're going to go ahead and take a look at kind of the framework for what the definition of a definite integral is and where it comes from. So we're going to use those ideas from the last couple of days, review, and then move forward. So a little bit of review, help me out. First notation here. Integral f of x dx is called what? I'm hearing whispers of it. It's called an indefinite integral. And that symbol as a command means what are you supposed to do? Find an antiderivative. Good. Okay. And that general antiderivative, if all we had was f of x, what notation did we use for the antiderivative? Big F. Your English teacher would say capital F. But yes, big F. Plus C, the constant of integration. Okay? If we think we know the antiderivative, how can we check to make sure we got the right one? Take the derivative. And that was based on the idea that we are more comfortable with derivatives at this point than we are antiderivatives. If you take a derivative, take derivatives, take the derivative of capital F, you should get lowercase f back. Okay? Then, that makes sense so far? After that, we went to this area idea. We started with a really basic example. We said for 3 hours, you travel in a car at 75 miles per hour. How far do you travel? We'll do the arithmetic for you. 225 miles. And we started to develop the idea that the area under a velocity curve will be the displacement. Okay? And then the idea was presented that what happens if we've got a velocity curve that changes? How can we find an area under a curve when geometry fails us? Because we don't have a formula for a shape that has a weird edge like that. Okay? And where did we go? What did we do? We drew rectangles, and we called them Riemann sums. Some dude named Riemann decided it would be a great idea to add up rectangles, and he became famous. How cool would it be if you were Riemann, and all you did was decide to add up rectangles, and that made you famous? How great would that be? He's got sums named after him. Of course he's famous. They're called Riemann sums. So the question, is Riemann famous? Is Pythagoras famous? He's got his own theorem. Well, he was. He's dead now, but... Okay. And we did rectangles. We did LRAMs, RRAMs, and MRAMs. Okay. Basic idea would be if you have 3 intervals and you have an interval, or you have 3 rectangles on an interval from 0 to 3, you would draw 3 rectangles, look at x squared. If we were going to do an RRAM, you draw up to the curve, go horizontal across dx, and so on, right? There's an RRAM. Really important moving forward to highlight this idea. Every rectangle is composed of a width and a height. The width we always call delta x. The height we use the function value to get. Okay? Whether we used a function value on the left, or a function value on the right, or a function value on the middle, we used a function value. Okay? Now I want to introduce you to the idea. This is not going to be crazy, but we used lefts, rights, and midpoints. Why? You could say because it was easy. Go ahead. Because it was easy. We used lefts, rights, and midpoints because it was easy. But who says that for this rectangle, that the right, or the left, or the midpoint's the best representative of the function? Couldn't we arbitrarily choose any value within that interval as an approximation? Couldn't I go like right here at 2.6 And wouldn't that rectangle also kind of approximate the height of the curve? Okay? So there's nothing, so part of today is there's nothing magical about the width of the interval, and there's nothing magical about the height of the function other than the fact that the height of the function has to be within that interval, otherwise it's a bad approximation, right? Okay? So the idea here is we're using some measurement of width and some arbitrary choice of a function value for height. That's all we're doing, and you could do it any way you wanted. Pick any function value in the interval. And the other big idea here at this point is we've always dealt with functions that are above the x-axis. And all good functions are above the x-axis, right? No. There's functions that go below the x-axis. So here's what I want to go with. Okay, this is where we're going to get into stuff that's just a little bit new. I want you to make a little bit of a change because this interval is really weird. I want you to make this interval from 1 to 5. We're going to make a right rectangular area approximation method. So on my drawing here, I'll pretend that this is 5 over here, and I'll draw my first rectangle. Remember, when we do RRAMs, we start on the right, don't we? We start on the right, and we go to the function, and we go, let's see, this is about 3, that's probably about 4, and this is 2, and we got 1 in here somewhere. It's not a great scale, but life goes on. Okay, what's weird about this? It's approximately the rectangles I would use if I was doing an RRAM. What's wrong with this? What's different? Kind of already said it. The rectangles are where? Below the x-axis. So if we use that idea of delta x times a function value, what are all the delta x's in this problem? What's delta x here? 1. What are these function values? Negative values, right? So the Riemann sum here would be, the right-handed Riemann sum here would be 1 times 3 plus 1 times 0 plus 1 times negative 2 plus 1 times negative 5. And the Riemann sum value would be 3 minus 2 is 1 minus 5 is negative 4. The value of the Riemann sum is negative 4. Now, numerically, that's not a problem. But looking at the picture, what's weird about it? Maybe you don't have the same preconceived notion about area that I do. What's the preconceived notion about area that I can't get past right now? Area isn't negative, right? Okay. So a Riemann sum, which up to this point we used to approximate the area under the curve, now gave us a negative value, which makes us a little anxious because area can't be negative. But I'm going to tell you right now it's not a big deal because it happens all the time. Okay. And yesterday we introduced the idea that a Riemann sum approximates a definite integral, right? So I want to show you this really briefly, and I think this will make things make a little bit of sense. I'm going to graph the sine curve. And I'm going to use the calculator to find the area under the sine curve. What's the area under the sine curve from, let's go 7 here, and let's go from 0 to 2 pi. What's the area under the sine curve from 0 to 2 pi? So those of you that are saying 0, area can't, why, there's area there. How can you tell me the area is 0? Okay. Those of you that are in physics are laughing at me right now. But if we go from 0 to 2 pi, it shades it, and it tells us the value of that integral is 0. What happened? This happened. So from here on out, and we haven't been below the axis yet, so that's why this is new. It's not hard to understand, but from here on out, if the curve goes below the axis, you're going to be adding negative area. Is that okay? We'll connect to distance and displacement in a minute. Okay, so add this to your notes. When the function is greater than 0, a Riemann sum, I didn't spell Riemann correctly, but a Riemann sum will contribute positive area. Okay? And when the function is below the axis, function is less than 0, a Riemann sum will contribute negative area. Okay? And those of you that are in physics are going to be okay with this. Those of you that aren't in physics yet, you'll probably be okay with this too. Okay? So, big vocab term for the day, or big vocab phrase. Net area versus total area. What a Riemann sum will always give you is net area. Okay, because a Riemann sum is restricted by the fact that it's got to use a delta x and a function value. And function values can be positive or function values can be negative. Okay? And we're going to compare that a little bit to the idea of distance, add up all the areas. So in example 2 here, you have a 10 and a 30 and a 50. What's the net area under this curve? Because the Riemann sum would give you positive 10 plus negative 30 plus positive 50, right? What's the total area? Total area is bigger than that. Total area is 10 plus the absolute value of negative 30 plus 50, which would give you a total area of 90. Okay? Now, you don't think of the absolute value function on that 30. You just make the 30 positive and add it, right? Your mind is an incredible calculator. It understands absolute value. Okay? Now, if we were to think of this in terms of displacement, if I started here and I moved to the left 2 meters, and then I moved back to where I started, what's my displacement? 0. Why is my displacement 0? Because I end where I started. But what's my distance traveled? 4 meters. What does my velocity curve look like? My velocity curve looks like some above, some below, and those two would be the same value, and then my displacement would be 0, so the value of the definite integral would be 0, and my distance would be 4 meters. Okay, except that would be according to my example. So with example 2, we're going to end up using those same 2 numbers. So net area is equal to displacement, and total area is equal to distance. All right, so this is the theory behind the definition of the definite integral. So a couple of assumptions. We have always used equal partitions. Do we need to? No, we don't need to. We've typically chosen left points, right points, or midpoints in the interval. Do we need to? No, we don't need to. Left, right, and mid were chosen just so that we could find nice function values. And f of x has always been positive. Does it need to be? It doesn't need to be. Okay? Now, for drawing purposes, we typically do f of x being positive. So, here's what I'm going to do. I'm going to kind of develop the idea of how a Riemann sum turns into a definite integral. Okay? I am going to take and I'm going to approximate the area under this curve between A and B. Now, I know that A looks a lot like 0, and we're going to treat A a lot like 0 here in a minute, but this could be done arbitrarily on any interval. Okay? And I am going to approximate that area using n sub, I got to spell subintervals, right? N subintervals. They're going to be rectangles. They're not always necessarily going to be the same width, but for the purpose of this, we will assume they are. So if I'm going to do n subintervals on an interval that goes from A to B, what's delta x? I'm hearing it. B minus A divided by n. Okay? Doesn't have to be that way, but we're going to assume delta x is consistent all the way across here. Okay? Now, I'm going to do an RAM with n rectangles. I'm not going to draw n rectangles because I'm not really sure I know how to do that. How do you draw n rectangles? You draw one more than n minus 1 rectangles? I'm going to do an RAM, so I'm going to start on the right and I'm going to draw a rectangle. I'm going to go over delta x. I don't know. How far is delta x? I don't know. Whatever looks good for you on your paper. I'll draw another one over here. And just for fun, I'm going to draw one over here. Okay? We're generalizing now. It's not very often in your mathematical career you have to generalize. Well, until you take a real analysis course in college, but that's the class that makes most math majors go crazy. That and differential equations. All right. Make sure I'm singing the right song here, guys. Okay. So let's do a Riemann sum. Let's go left to right, because that makes sense, right? What's the area of the first rectangle? Okay, let's go width first. How wide is it? Delta x. How tall is it? Let's assume that A is 0. That makes this easier. How far did we go to the right? Delta x, right? How far did we go up? F of delta x. Is that okay? What's the area of the second rectangle? How wide is it? Delta x. How tall is it? F of 2 delta x's. Does that make sense? The second rectangle is 2 delta x's out, and F of 2 delta x is high, right? Okay. Third one, you'll notice a pattern. Delta x times F of 3 delta x's, right? How many of these are we doing? N of them. So this is notation for n of them. I'm going to do the nth one now. Delta x times F of n delta x. This is us generalizing as much as we can. Okay. This can be written, and this is new notation for some of you and not new notation for others. I understand that there's a difference between honors pre-calc and how they cover this, but you're not going to be at a disadvantage if you don't know this yet. This can be written as a sum from I equals 1 to n. This sum means I'm going to add up a whole bunch of terms that have a similar pattern. F of delta x. I'm sorry, I need to hold on a second. F of I times delta x times delta x. Let me pause and make sure that's right. That's right, yeah. Okay. So what that means is start with 1 and put in 1 for I, and that's your first term. Then you're going to add to that the value when I is 2 delta x's. Then you're going to do 3 and 4 and 5, and you're going to have a term for every one of these all the way up to n. That is sum notation for the Riemann sum that approximates the area under that curve. We're all good with that? Okay. We came to the conclusion a couple of days ago that if 2 rectangles is good, 4 rectangles is better, right? And what's better than 4? 8, 16, 32. What's the best number of rectangles you can do? An infinite number of rectangles. N rectangles, if n is really big, is a pretty good number of rectangles, right? Okay? But we all have to agree that the more rectangles you have, you're going to have a better approximation, right? We would love to have an infinite number of rectangles. Can we add up an infinite number of rectangles? No, we cannot. You don't have enough time to add an infinite number of rectangles together. But we want to pretend that we're going to add up an infinite number of rectangles. What's mathematical notation for we're about to pretend we're going to add up an infinite number of rectangles? Okay, forget about the infinite number of rectangles. Let's pretend we're going to go towards infinity. What's mathematical notation for that? A limit. So now we're going to take one more step here. Since we all agree that the more rectangles, the better, I'm going to put a limit in front of this thing. The limit as n approaches infinity. N is the number of rectangles. The limit as n approaches infinity of this sum, I equals 1 to n, f of I times delta x times delta x. Here's the magical moment for today. I'll let you get that notation down. Okay. This Riemann sum approximates the area under the curve. And we all agree that for a big value of n, this would be a really good approximation, right? We can't do a really big number of n. We could do a big number of n, but we couldn't do an infinite number of n, right? So we're going to make it a limit. This is defined as the value of the definite integral from a to b of the function value times dx. Okay? Where's the dx probably come from? Where does this dx probably come from? Probably that, right? Delta x was the width of a rectangle, dx represents the width of a rectangle. F of I delta x probably represents f of x. So this symbol represents the height of a rectangle. Of course it does. It's the height of the function, right? That makes sense? And this right here represents the width. Okay? You kind of probably already assumed this from what we've done over the last couple of days. But a definite integral is the same as a sum of an infinite number of rectangles. And that's a little bit of a weird concept to grasp, but it was really weird when we had 2 points and we moved one of them infinitely close to another, and we went from a secant to a tangent. Remember that first semester? That's the same idea. What's calculus about? It's about taking ideas that you can't do and doing them anyway because you feel like approaching infinity. That sound fun? Can't do that. Well, I can try. I can pretend. Okay. And the other thing, too, is when we draw this integral symbol, I always draw a stretched out S. And when I think of S, I think of sum. Okay? So that definite integral is a sum. Weird tricks to remember what we're doing here. Questions so far? All right. So I want to give you a heads up on this thing. I used as few symbols as I could to make the notation that I made at the bottom of this page. Okay? I used fewer symbols than the book used. I think it's important to note, and we've already talked about it, but I want to show you where it applies. In the book's notation for the definite integral, they do a couple of things different. They let delta approach 0. What's the difference between letting delta x approach 0 and letting n approach infinity? It's the same idea, right? Letting the width of a rectangle approach 0 means you're going to approach an infinite number of rectangles. Letting n approach infinity is the same as letting the rectangles be thin. So that's a little bit different that they use. Not a big deal, right? Okay. The other thing they do is they do a sub k on their delta x's because what they're trying to do is they're trying to allow for a different rectangle width if you need to. Not all of your rectangles need to be the same width. But if you let whatever their widths are, if you let their widths approach 0, they're all going to end up being the same, right? Okay? And they do the same thing with this x sub k with an asterisk by it. What they're saying, we did an RRAM, they're doing any point on the interval. I think it's just as easy to do it as an RRAM than to think about it as, well, you could have used any point on the interval. Okay, we talked about that a little bit already. When it exists, this integral equals the net area of the region bounded by the graph and the x-axis. Okay? We've done Riemann sums to pretend we knew how to find the area, and now we're going to do definite integrals. We're not going to evaluate these by hand yet today. I showed you the other day on a calculator, but I'm going to show you a couple other little things that are going to be important when you come to the AP exam. Okay? What's the big idea here? The big idea is you're doing a sum of rectangles. And you need to know that an integral represents an area. Integrals equal area. Integrals equal area. Integrals equal area. You're adding up rectangles. Okay? AP does not require, I'm going to go on to example 3 now. AP does not require that you know how to evaluate Riemann sums. So when they give you this thing, this Riemann sum, they don't actually ask you to find that Riemann sum and then use a limit. They're not asking you to do that. They're asking you to recognize that this limit of this Riemann sum corresponds to a definite integral. And it's easier than you think. So when multiple choice comes up on the AP exam and you see a limit that involves a sum, you don't really want to calculate the sum. We're not going to really even show you how to do sums. You want to be able to recognize that that sum is the same as the value of a definite integral. And let's talk about that integral. What is it? What would you suppose that integral would be? Let's do bounds of integration first. What's the interval? What should I put at the bottom? -1. What should I put at the top? 3. This is referred to as the lower limit of integration. This is referred to as the upper limit of integration. Like we talked about in the calculator yesterday, when you did the calculator approximation for the area, you had to find a lower limit and upper limit. I'm not wild about it because when I think lower, I think this, and upper, I think that. But with integrals, you got to think sideways. Lower to upper. You're always going left to right when you're doing integrals. Okay? What do you suppose the function is? Don't overthink it. It is what you think it is if you look at it. 3x squared minus 2x plus 5 dx. Okay? I'm not going to ask you to evaluate that today, but there are a couple of homework problems that ask you to go from a Riemann sum limit to a definite integral. You just have to write the definite integral. Okay? Good so far? Okay. Another strategy that's going to help you is understanding the idea that what is a definite integral at this point? What do we know about definite integrals? They are area. So if I don't know anything about that symbol right now, other than the fact that it represents an area function, what should I do? Let's draw a picture. Here's our function. Let's do the axes first. It's not an x, it's a theta this time, so let's call this theta. Let's call this f of theta. What does the function pi over 2 look like? Just a line. What kind of a line? This is like y equals pi over 2, isn't it? Let's say this is pi. So pi over 2 is like right here. Right? What's my interval that I care about? -4 to -1. -4, -1. Do I know the value of that integral even though I don't know how to evaluate an integral? This distance is 3. This distance is pi over 2. this is going to be the fastest way, if you can, to evaluate an integral. Just find the area. That's a handful of your homework problems tonight. What's the easiest way to evaluate an integral? Find an area. It's pi over 2 times 3. Yep. So because this distance is 3, that height is pi over 2. So the area, yeah, I didn't draw that very well. So it's 3 times pi over 2. Good drawing right over here, isn't it? It's really good. Good so far? Let's do another one. Mr. Best, you haven't taught us how to do integrals yet. But what is an integral? It's an area. It's an area of what? I don't know. Goes from -4 to 0. What shape is that? What is this thing? Okay, should I do some algebra to help? Recognize it yet? It's a circle with radius 4. Okay, but in this case, because this is a function, it's a function of x. It's really just the positive part of the circle. So we're looking at this thing. And since we're going from -4 to 0, we're really just finding that area. Can you find that area? Go back to geometry. What's geometry tell you about that area? What is it? It's a quarter of a circle, right? It's a quarter of pi r squared. 1/4 times pi times 4 squared. The value of that integral is 4 pi. Okay? So over the next couple of weeks, I'm going to teach you some other ways to evaluate integrals. But I want you to have this in your back pocket in case this becomes the easiest way. Because on a multiple choice test, if this was on the multiple choice portion of the exam, there is a way to integrate this and do this calculation by hand, but it's not as easy as drawing a picture and finding the area. I want you to keep that in your back pocket, because sometimes they'll trick you into wasting time, like doing an analytical method when you really could have just drawn a picture. Question? No? Good? All right. Last idea. We talked about differentiable. Now we're going to talk about integral really briefly. You don't have to have a formal understanding of this, but functions are integrable under the conditions that it's continuous on a function, or if it's bounded on a function with a finite number of discontinuities, which means you can have jumps. You can integrate functions that have jumps. You can't differentiate them, but you can integrate them. Then f is integrable, that's a mouthful, on AB. If it's continuous, it's integrable. I still have a hard time with integrable. Polynomial functions, duh, of course they're integrable. That's what we've been doing for the last couple of weeks. Sine and cosine functions, of course, they're smooth, they're nice. Now, rational functions are also integrable, provided that it doesn't have any points where the denominator is 0. So asymptotes are a bad idea. If I make a quick drawing here of the function 1 over x, just throwing it out there, why is it a bad idea to find the area between 0 and 3 on this function? What happens here? We got an asymptote. There's not a bound on the area. Okay? There are going to be some methods to approximate that, but we're not going to go there just yet. Will you do some things on your homework outline for me? Will you cross out number 6? It's okay, it's not great. I think it's worth reading the question. It's not worth spending a lot of time on, and I think it's more confusing than it's worth. Will you also skip problem 17? It asks you to use rectangles it asks you to use 4 rectangles on an interval that goes from 0 to 3 pi over 4. And that's not really nice intervals for making rectangles on, because your delta x is 3 pi over 16. Anybody interested in a delta x of 3 pi over 16? Yes? No? Good, skip 17. And then on some of these, and I think it's mostly in this range from 14 to 18, they ask you to find an LRAM and an RRAM and an MRAM. I don't want you to do all of those because I don't think it's worth your time. But the point of the problems in here from 14 to 15 and 18 is they're going to start giving you functions that might do this. And they want you to draw, they want you to see what it looks like to have rectangles that are not always above the axis. So don't do the LRAM, the RRAM, and the MRAM. Pick one. Do LRAMs. Doesn't matter. Do MRAMs. Well, LRAMs and RRAMs are probably easier. So whatever you'd like. Can I give you one joke to send you on your way? Wait for it. Thoughts? Anybody want to take a chance? Some people in the back shaking their heads. You know the answer to this? No thoughts. What's the antiderivative of 1 over x? What is it? What is it? It's not log cabin, but it would be funny if the answer was log cabin. It's even more funny when you get the real answer. It's not a natural log cabin. Guys, you're forgetting something really important. And any joke isn't very good if you have to explain it. It's an indefinite integral, and when you have an indefinite integral,